All right, guys, so this will be about the electromagnetic spectrum, which you guys are probably familiar with, and color. So I want to talk a little bit about color. And so I'm hoping that at least the color portion will be new for you guys. Color is one of the main ways that we kind of encounter light in the world around us, unless you're doing kind of experiments with prisms and rainbows and so on and so forth. But yeah, so color I think is very interesting, and how we perceive color is kind of cool too. So I'm going to talk about that in this video. But first, let's get to a little bit of the sciencey stuff. So when we look at the electromagnetic spectrum, there's a whole range of these wavelengths and frequencies, and so these go from very long wavelengths. These are like radio waves. The wavelength 10 to the third, so this would be like on the order of kilometers, hundreds of meters. Okay, so very, very long wavelengths, and these frequencies, um, are fairly low. So 10,000 hertz, 10,000 cycles per second. Okay, and this goes all the way up to 10 to the 20th hertz. So there's quite a range here. Um, so anyway, so it goes from radio all the way through gamma rays, and one of the things I want you guys to know is that all electromagnetic radiation moves at the same speed. Okay, it all moves at the same speed. And that speed is the speed of light. So because this is so common in physics, the speed of light, we give it the symbol c. So it has its own symbol c. And the symbol c, we've seen this before in some of the problems I've given you. It's going to be 2.998 times 10 to the 8th meters per second. Okay, so this is the speed of light. We'll talk a little bit later when we talk about relativity. This is kind of like the speed limit. This is the fastest that any particle, as far as we know right now, this is the fastest that any particle can go, and it has to be a massless particle. So we'll talk about that later when we talk about relativity. But for right now, I want you guys to know that all of these waves travel at this speed right here. The speed will be given to you on the test, by the way. You don't have to memorize it, but you're going to use it enough and you probably will end up memorizing it. The other thing is that the wave equation still works. Okay, so the wave equation still applies. So just to remind you guys of what that wave equation is. So the wave equation still applies. So this equation, remember, is, before we saw it is speed is equal to frequency times wavelength. Now we're going to see a little bit differently. Since this speed is c, we're just going to say c is equal to frequency times wavelength. So again, this is the speed of light, and we'll use that right there. So our speed of light. Okay, then the frequency is in hertz, and the wavelength is in meters. Okay, so we can still use this equation in order to calculate, the properties of this electromagnetic radiation. So we have radio waves at very long wavelengths, and then microwaves will be a little bit shorter wavelength, higher frequency, and then infrared. We kind of perceive this infrared. Let me change the color here. So we perceive this infrared as heat very often. Okay, so this is how we perceive heat. There's this little tiny sliver in the middle. Even this is exaggerated as far as range goes, but this is what our eyes can perceive. Okay, this is what we can detect with our eyes. And then ultraviolet radiation, this is what gives you sunburn. That's a little bit lower in wavelength and higher in frequency. And then we have X-rays, and then we have gamma rays. So these gamma rays come from very violent explosions. They come from radioactive decay. So these are very energetic type of things. And one of the things that we're going to learn about later is that the higher the frequency of the electromagnetic radiation, the higher the energy is. Okay, we'll see that when we start talking about quantum mechanics. Okay, so those are kind of the mathematical, physicsy type of stuff. So let's talk a little bit about color. Okay, so what we have here, what I'm showing you here, are these three peaks. Now, these three peaks correspond to the cones. Okay, so in our eyeballs, if you think, our eyeballs, okay, there's kind of our eyeball, and there's like this optic nerve coming out of the back. There's our retina that kind of coats the back of this eyeball. And in this retina, we have cone cells, which perceive color. Okay, we need these to perceive color. And then there's also rods which detect brightness. Okay, so they don't detect color, but they can detect brightness. And so if you didn't have any cones, you just had rods, you'd see in black and white. You could see, light and dark, but you couldn't see any color. So what these peaks are showing you kind of where the three types of cones in our eyes absorb. So in our retinas, there are three different types of cones. There's a cone that absorbs kind of this bluish light, a cone that absorbs this greenish light, and a cone that absorbs kind of this orangish red light. And so you see underneath these curves, they kind of cover the entire visible spectrum. And it turns out that our perception of color has to do with how well our cones, pick these up. So for instance, if we see a color and we have the red cone and the blue cone firing at the same time, then what we will perceive is this magenta. Okay, so there's this magenta color. If, however, it's this red light, then this is going to be the only cone. It's going to be over here, and so this is the only cone that gets absorbed. If it's in here, so if we have kind of a green and red, we're going to perceive yellow. Okay, our brains process it as a yellow color. Okay, over here, we'll have green and kind of this bluish color, and then we have kind of a light blue or cyan here. So this is what allows us to perceive color, is different intensities of the wavelengths combined. Our cones pick that up, they send it to our brain, and we process that as different color. And so we have, red, blue, green, magenta, cyan, and of course this is yellow. Okay, comes from the overlap of colors. Now, an interesting thing is you may have heard of color blindness, and for all I know, some of you guys may actually be colorblind. If so, I apologize for this video. It's going to be kind of hard to follow. But the red and the green, notice how close these peaks are. What can happen genetically is sometimes these cones, they kind of overlap. So there's not a large separation between them. And we require the separation in order to differentiate between red and green. If these don't overlap, if these overlap too much, okay, then what happens is that we can't differentiate between red and green, and so we won't be able to perceive them, and then we're red-green colorblind. Okay, so that's the cause of color blindness, is genetically these cones, they absorb just a little bit off, and so it's very hard to pick out between red and green. However, you might have seen some glasses, they do sell glasses, and they kind of filter out this part, so they kind of block out this part right here where they overlap, which makes it easier for the cones to pick up these different colors and allows the people to see color. In other words, there's no interference going to the brain. Okay, so this is how we perceive color. Again, there's three different types of cones. They absorb in three different regions. They absorb light in three different regions, and then the mixture of the nerve signals from these three different cones gives us the perception of color. And then the rods, is the whole dark and light perception. It's the sound testing perception. Okay. Now, when we talk about color, as kids, we play with crayons and we start to say, oh, if we mix like yellow and, if we mix yellow and red, we're going to make orange. Or if we mix like yellow and blue, we make green. And that's what we get used to, but and it's not wrong. But there's actually two different ways to create color. One is called additive and one is called subtractive. So additive would be combining light together. So you have different colors of light that combine and overlap. And this is what we were looking at before. So if you have a green light and a red light shining at the same spot at the same time, again, what will happen is that these cones, these M cones and these L cones, will start firing at the same time, and our brain interprets that as a yellow color. Okay, so that's adding. We're adding these light colors together to give us yellow. And then you can see the green, blue, red, blue. Okay, so we have red, green, blue are called the primary colors for light. Okay, red, green, blue. And then cyan, yellow, and magenta are the secondary colors, okay, because they're mixture. And if we have all the light colors, if we have red, green, and blue, or we have these all at the same time, we get white. And interestingly, we need red, green, and blue to create white. We need all three of these. However, if we combine cyan and yellow together, so if we had like a cyan light and a yellow light and combine those, we would still get white. because the yellow is a mixture of red and green, and the cyan is a mixture of blue and green. Okay, so we only need 2 secondary colors to create a white light, but we need all 3 of the primary colors to create the white light. Now, over here, okay, so this is light, and this would be paint or pigments. Okay, now what goes on in pigments, and the way you should understand this, okay, is, and let me change the color here so you can actually see it. When we see yellow, that means that the paint absorbs all colors but yellow. Okay, so it absorbs all colors but yellow. So looking over here, we see that if we perceive yellow, okay, if we're seeing yellow, then that means that it's absorbing the blue, okay, and essentially it's reflecting out the green and the red. So this yellow light that we see is a combination of these two. Okay, so it takes all the blue out, it absorbs all the blue, and it sends off the red and green. You can kind of see that here. So yellow and blue, these are on opposite sides, cyan and red, magenta and green. So this color on the opposite side, these are called the secondary pigments. This is the light that gets absorbed by the primary pigment opposite that. Okay, so yellow absorbs blue, magenta absorbs green, cyan absorbs red. Okay, which means that if you have a yellow pigment, which is absorbing all the blue, and a magenta pigment, which is absorbing all the green, okay, so the yellow pigment absorbs this, the magenta pigment absorbs this. The only thing left to be reflected is this red color right here, and that's what we get, what we see here. So red, green, and blue are actually the secondary pigments. Okay, and that's not really what we're taught. We're taught that this red, green, and blue are actually primary colors, but red, green, and blue are secondary pigments, okay, because they come from the combination of 2 of the 3 primary pigments. And again, what we can see is that if we have yellow, magenta, and cyan, if we have all 3 together, we absorb all the light, and we get a black pigment, okay, because all the light's being absorbed, whereas we only have 2 of it. So if we combine red and green together, we'll get black, or red and blue will get black as well. Okay, so that is how we see and perceive color, and the difference between the additive color mixing, where we keep on adding light in order to get a color, and subtractive color mixing, where the pigment absorbs some color light and reflects what's left. So it subtracts out what it absorbs, and what we see is what's remaining. So I hope that makes sense. If you guys have any questions, please let me know.